Now, there's a pretty good chance you've seen at least one video about axial flux electric motors and how amazing they are supposed to be. So in today's video, I'd like to take a closer look at this type of motor. So we're going to see what it actually is and why you might want to use it. Now, the kind of electric motor that you're probably most familiar with is called a radial flux motor. So I've actually got a whole bunch of motors here on my desk. This is an example of a radial flux motor. So in this case, we've got the rotor, which is the part that rotates, and the stator, which is the part that remains stationary, and the rotor rotates on the inside of the stator like this. So this is the type that you've probably seen the most, but you can also have a different kind of radial flux motor, which is this guy over here. So in this case, we have the stator on the inside, and the rotor is actually a hollow cylinder that rotates round the outside of that. So this is generally called an outrunner style motor, but there's still radial flux. Then you can also have an axial flux motor. So an axial flux motor, and I've also got an example of that, which is you might actually remember this one. This is the DIY electric motor that I built for my video on switched reluctance motors a while back. And this is an axial flux design. So in this case, the stator and the rotor are placed side by side, rather than one being inside the other. So that is what axial flux means. So it purely refers to the physical layout of the parts, and not really to what the working mechanism of the motor is. So in this case it happens to be a reluctance motor, but it could also be a permanent magnet machine or an induction motor, and similarly it could also be either brushless or brushed, so all that variation still exists within the axial flux layout. Also, you can have different sort of sub-layouts, I guess you could call them. So just like with the radial flux motor where I showed you the in-runner and the out-runner, with axial flux you can also have that kind of thing. So here we have one stator and one rotor next to it, but you can also have two stators with one rotor in between, or two rotors with one stator in between, stuff like that. So now that we know sort of what it is, why would you actually want to use this? To understand this, we have to go back to the basics of how an electric motor actually works. So the torque production of an electric motor can be explained using a phenomenon called the Lorentz force, which in this context means that if you have a wire that carries an electric current and you place that wire in a magnetic field, there can be a force applied to that wire. And a quick way to find the direction of that force is using something called the right-hand rule, which you might be familiar with, which tells you that in a situation like that, the force applied to the wire is always perpendicular to both the magnetic field and the electric current. So here's a little example for a bit of context. So let's say that we have a magnetic field which goes into the whiteboard. That's what these little X's mean. And in that magnetic field is a wire, like this, in which we have an electric current going this way. Now that means in this case there would be a force acting on the wire pointing in that direction, so pushing the wire up. And that's the force that moves an electric motor. The magnitude of this force depends on a couple of things. First of all, it depends on the strength of the magnetic field. It also depends on the amount of current in the wire. And it depends on the amount of, the length of this wire, so the amount of useful or active length in the magnetic field. So if you want to improve the torque of an electric motor, assuming that the magnetic field remains the same for a bit, there's two things you can do. You can increase the active length, which basically means make your windings bigger, or you can increase the thickness of the winding so that it can handle more electric current. Either way, you're adding more material to the motor. You're making the windings thicker or bigger, so you're going to make the motor bigger as well. So you could say that torque output is roughly proportional to physical size. Now, you might also say, well, what about adding more turns? Because in a real motor, you're not just going to have one wire, it's going to be part of a coil. There's going to be more turns of this. Well, that doesn't really matter. Purely in terms of maximum torque, it doesn't matter if you have a super thick bar of copper like this, or a bundle of wires with the same thickness. Ultimately, it has the same net current capacity. Okay, so the next thing we need to talk about is how not every part of a winding in an electric motor is equally useful in making torque. So what do I mean by this? Well, let's say we have a section of a motor like this. So could be an axial flux motor, could be a radial flux motor, doesn't really matter for this. So we have a couple of permanent magnets. So there is a north pole over here, and there is a south pole over here, and then we have a winding sitting right in front of that, like so, with the electric current going clockwise. Now I'm just going to say that, for argument's sake, this is an electric motor that is able to move in this direction. So that's the direction that it can mechanically rotate in or slide in. If it's a linear motor, doesn't matter. So either the winding is able to move side to side, or the magnets are able to move side to side. Now, if you apply that right-hand rule to this side of the winding, you're going to find that it produces a force in this direction, so to the right. And if you apply the same thing to this side of the winding, you will also find a force in this direction. So in other words, the winding wants to move this way, or the magnets want to move that way, which is great because that's the torque production of our motor. But now let's say that you applied that same right-hand rule to this point right here, so to this little part of our winding. Well, you'd find a force sort of pointing in that direction, which is useless because that's not a direction that our motor is able to move in. So that force does not contribute to the torque production of the motor. And what you'll find is that all the parts of this winding that run in the same direction that our motor is able to move in don't contribute to making any torque. So those are what you could call the inactive parts of the winding. And of course, if you want to make the most efficient use of the materials, then you want to minimize the amounts of inactive copper that you've got in there. Not only because copper wire can be expensive, but also because that is unnecessary electrical resistance which negatively affects the performance of your motor. We can also see this in one of our real electric motors over here. So if we take a look at this little motor again and just pull it apart, if you look at the stator right there with the coils, you can see that these parts, so the horizontal sections of these windings, they are perpendicular to the direction that the motor rotates in. So those are the parts that contribute to the torque production, the active parts of the winding. But these bits, where it sort of wraps around the ends, also referred to as end turns, those are the inactive parts of the winding. They are not pointing in the right direction to make the torque. Now, in this particular motor, the vast majority of the copper sits in those horizontal slots, which means that this motor is using the material rather efficiently. But what would happen if I start making this motor shorter, so I start reducing the length? Well, in that case, those horizontal sections will start getting shorter and shorter, but the end turns remain the same, and so the ratio between them gets worse, and the proportion of inactive winding increases, which is bad. So this is where an axial flux design can come in really handy. This is because on an axial flux motor, the coils are placed, well, axially. So changing the length of the motor does not change the shape of your windings, and therefore does not change the ratio between the active and the inactive parts of the winding. So take a look at this little picture that I have made of an axial flux, or part of an axial flux stator, which has these coils like this. Now if you change the length of the motor, which is into or out of the whiteboard, it doesn't change the shape or the aspect ratio of those coils, and so it doesn't change the amount of inactive versus active copper in the motor. And that makes it an ideal choice for creating a very short electric motor. Now there is a bit of a misconception that I've seen about this, which is where people will argue that in an axial flux design there is no inactive part of the winding at all, like all of the winding is used. But that is not the case, because we've still got parts of that coil that point in the same direction that the motor is moving in, and so those parts of the coil, the top and the bottom in this case, do not contribute to making any torque. So the inactive parts definitely still exist. It is just that the ratio between the active and the inactive parts is constant when you change the length of the machine, and that becomes an advantage at very, very short machine lengths. So this is why, for designing a very, very flat or very short electric motor, it makes sense to use an axial flux design. Now, something that I'd also like to discuss is that in a bunch of these videos and articles that I've seen about axial flux motors, they will mention at some point that in an axial flux motor, torque is proportional to radius cubed, whereas in a radial flux motor, torque is only proportional to radius squared. But they'll never really tell you how they got to those numbers, so I'd like to investigate that a little bit better. So what I've done over here is, as you've already seen, I've drawn part of an axial flux motor and part of a radial flux motor. So on this side, we're simply looking at the front of an axial flux stator. You can see we've got those windings. We already talked about that. And then on this side, we have the radial flux machine, where we have a stator on the inside and then a rotor on the outside. So this is an outrunner style motor, just like this one over here. And the windings are these things that you're looking at like this. So we're looking at a cross-section of the windings. The windings are sort of running into the whiteboard. Okay, so let's see what happens if we double the radius, or the diameter, of an axial flux machine. So we're just going to say axial flux at 2 times the radius. What happens? Well, first of all, we get 2 times the radius, so the coils are going to stretch out like this, so they become twice as long, so we get 2 times as much active length. Okay, so I'm just going to say L equals 2 times the active length. But also, everything is going to get twice as wide on this face, because, you know, not only in this direction does it scale up by 2, but also in this direction. So the windings also get twice as wide or twice as thick. So we're just going to write down a little square, which I'm going to use as the symbol for the cross-section of the winding. That's also going to go up by 2. Now let's assume that because we have twice as thick wire, we can also run twice as much current. So I, the electric current, is also going to be 2. So what we have now is we have twice the active length, we have twice the electric current, so that should give us 4 times as much force. But on top of this, we have twice the radius, so the force is acting 2 times as far away from the shaft of the motor, so we get twice the leverage, effectively, which means we have to multiply by 2 again, which gives us a torque that is supposed to be 8 times as much. Okay, so now let's do the same thing for our radial flux machine over here. So in this case, again, radial flux at 2 times the radius. What will happen? Well, first of all, the active length in this case is going to remain the same, because we're not making the motor any longer, and the windings run along the length of the machine, so the active length is just going to be 1. Like this. Now, the cross-section, however, is now going to be 4 times. This is because the surface area is proportional to radius squared, so for 2 times the radius we get 4 times the surface area, which includes 4 times the surface area for our windings. So we have 4 times as much cross-section, which also means, by the same logic, we should have 4 times the electric current, which means in this case we're going to have 4 times as much force, just like over here, and again also 2 times the radius, which means the torque is also going to be 8 times as much. But hang on a second, that's not supposed to be the outcome, because on this side, indeed, we expected the torque to be 8 times as much, because torque was supposed to be proportional to radius cubed. But on this side, we weren't expecting 8. We were expecting the torque to be proportional to radius squared, so it should be 4, not 8. So what's going on here? We must be missing something. And this is where we get to heat or power dissipation, because of course those windings are going to be generating heat, they're going to be dissipating power, and that power is equal to current squared times resistance. So over here, what is the electrical resistance? Well, first of all, we get twice the cross section, so the wire gets twice as thick, so we would get half the resistance. But we also get twice the length, the wire gets twice as long, which compensates for that again, which means the resistance will simply be 1. It'll remain exactly the same. But we are running 2 times as much electric current, so our power dissipation is going to be 2 squared times 1, which is 4 times as much. So I'm just going to write here P equals 4. So we're dissipating 4 times as much heat by doing this. Now what about this one over here? So in this case we have 4 times as much cross-section, which means we only have 1/4 of the original resistance, but we're also using 4 times the electric current, and current is squared in this formula, so that's pretty dominant, which also means that in this case we're still going to dissipate 4 times as much power, just like over here. Now we have to think about what surface area is going to be dissipating that power. So if you consider that an axial flux motor is pretty much shaped like a flat disc, so it only dissipates power through the front of the cylinder and the back of the cylinder, so the flat surfaces. Well, those surfaces are proportional to radius squared, which means that if you double the radius, those surfaces get 4 times as big, and so they can dissipate 4 times the power, which means you can get your 8 times the torque. Whereas for a radial flux machine, in a lot of cases, people will consider this part of the cylinder to be the cooling surface, so the round part, either round the outside or with an outrunner like this, maybe round the inside if it's hollow. And the thing is that that surface is not proportional to radius squared, that surface is simply proportional to radius. So if you get 2 times the radius, you also just get 2 times the surface area for cooling, which means you can only dissipate, in this case, 2 watts of power, which means you can't have 4 times the current, you can only have 2 times the current, and if you only have 2 times the current, you're going to have 4 times the torque, which is proportional to radius squared. So this is where that sort of reasoning comes from. But of course, it's not entirely correct, is it? Because this assumes that a radial flux motor can only dissipate heat through that round surface and not through the side, which in reality is not true. You can also lose heat through the sides of a stator. And actually the same thing applies for the axial flux motor. You know, this assumes that an axial flux motor only dissipates heat out of those flat sides of the stator, but in reality it also loses heat through the round surface round the outside. So if you do a more fair comparison where you use the surface area of the entire cylinder in both cases, well then again there is no difference between them. What is interesting though is that as you make the motor shorter so that it becomes more disc-shaped, the front and back surfaces of the cylinder start to make up a greater and greater proportion of the overall surface area, and therefore the math starts to become increasingly more like this. It's never going to be quite like this, because that would only be the case if the motor is a perfectly flat disc with no length at all, but the shorter you make it, the flatter you make it, the more the math starts to work out like this. And so there is a torque density advantage to making very flat, wide electric motors. And as we discussed earlier in this video, if you want to make a very, very flat motor, an axial flux design is usually the best way to do it. The final thing I'd like to talk about is power, because a lot of people suggest that axial flux motors have superior power density, but I don't really agree with that. So power is the product of speed and torque. So you don't necessarily need a lot of torque to make a lot of power if you have enough speed to make up for it. And a nice thing about having speed or spinning fast is that it doesn't come with a size penalty for the motor. And this is how it's possible for like tiny little drone motors and stuff to make thousands of watts of power. It's because they spin at ridiculously high RPMs, which is directly related, by the way, to high frequency transformers being smaller for the same amount of power output, which I talked about in a video I made a while ago. So the key to very high power density is running at very high RPMs. And if you look at the sort of mechanical design aspects, a radial flux motor design, you're usually able to get up to higher RPMs than an axial flux, which is sort of this wide pizza or pancake shaped thing. So from a power density perspective, a radial flux motor is usually the best option. So at the end of the day, none of these types of motors is necessarily the superior motor. It kind of depends on what you're going to use it for. It's just about the right tool for the job. Typically that means if you want a very, very short, wide motor, it's a good idea to go with axial flux. But if you need a longer motor, then a radial flux motor is probably going to be the best option. So it just really depends on what you're going to use it for, and none of these is necessarily always better than the other. Which kind of brings me to the end of this video. So I hope you've enjoyed watching it. If you did, then maybe click the like button or consider subscribing to this channel. And of course, thank you very much for watching.